Okay, let's restart our discussion of the BREMSSTRAHLUng, second most important way particles lose energy when they travel through matter. The point in the derivation and description of BREMSSTRAHLUng is that the fractional energy loss of a particle, for example an electron, where it's most relevant, is per unit length efficiently described by a radiation length. The energy loss per unit length is more or less proportional to the energy itself. So one makes an ansatz of the EDX equals minus E and then some proportionality constant of the dimension of a length. And if you integrate this differential equation, you get an exponent. So, and from this fact, you can already infer that x naught, or the radiation length, is the length over which an electron, for example, an electron's energy falls to a fraction of 1 over E, which is 36.7%. So a small radiation length means that by means of radiative energy losses, a particle is quickly stopped. If it is large, then BREMSSTRAHLUng energy losses are smaller and particles can travel further. I put to the right a table with material properties. We already know that BREMSSTRAHLUng is a coherent effect. It's coherent because it comes from the interactions come from photon exchange with the nucleus at energies where the photon does not resolve the constituents inside the nuclei, but interacts coherently with the whole nucleus, and hence the radiation length is very roughly inversely proportional to c squared. There's an empirical expression that that predicts the radiation length times density to within 2.5 or so percent, and it's there are logarithmic corrections that predict material dependent effects. The main feature is the 1 over c squared here. So, for example, in beryllium, aluminium, in low C materials, the radiation length is large. In high C materials, lead, uranium, the radiation length is very low. The quantities are given per unit density. That gives you a good comparison with respect to C, and for practical applications, it's of course important in the unit x naught in terms of centimeter is of course important. So beryllium, an electron can travel 35 centimeters until it loses 2/3 of its energy, and in uranium only 3 millimeters. So uranium high C materials have a much larger stopping power. The materials given at the top are conventionally used in calorimetry. For example, lead tungsten is the material used in the CMS crystal calorimeter. Iron is used in sampling calorimeters. It's not instrumented, but is used to stop radiation in case it is so desired. Then there are scintillators. We're going to discuss scintillation detectors. Here you have the lead tungsten average radiation length of 0.8 centimeters. And below here in gases, of course, these are normal conditions. That's 20 degrees Celsius and 1 bar. Of course, the stopping power is much lower, and conversely, the radiation length much larger. Again, the critical energy is defined as the energy where the BREMSSTRAHLUNG and the ionization losses agree. Ionization is dominant below the critical energy. BREMSSTRAHLUNG is dominant above the critical energy. It's important to realize that the critical energy is a factor 10,000 different for electrons and for muons. The critical energy is much lower for electrons because BREMSSTRAHLUNG is much higher for these lighter particles. Critical energy for muons is in the TeV or hundreds of GeV regime, as we've already discussed. So high C materials have a low critical energy because the ionization is incoherent, proportional to C, while BREMSSTRAHLUNG is coherent, it's proportional to C squared. So when you increase Z, BREMSSTRAHLUNG increases stronger than ionization. And that's a way to design a detector. The choice of the C of the material is the first consideration when choosing a detector material. You see here the EDX for electrons. There is a very big difference to the muon case. Here we divide by energy. So there is a large factor in the slope here missing because we divided out one energy dependence that we did not do for the muons. So you cannot overlay the electron and the muon case. Electron and positron interactions are very slightly different because of the positron annihilation in case of incident positrons. Otherwise, electrons and positrons behave very similarly. So we have the ionization loss that is declining here because we divide by the energy. It declines over the whole range. Then we have the BREMSSTRAHLUNG effect, and then we have smaller interactions, Möller and Barber scattering in case of electrons or positrons. So again, what happens if a highly energetic electron hits a material, it will enter somewhere here. BREMSSTRAHLUNG will be pretty high. It loses its energy, so it falls down here towards the critical energy. It will spend most of its time here and then be lost. So that's important for detector design, because if we have, for example, a photomultiplier or something with a sensitivity of for a certain energy, we can choose our we can choose the C of our detector material to match the sensitivity of our photomultiplier. And if we choose a higher C, then the BREMSSTRAHLUNG will move. The BREMSSTRAHLUNG process will be higher. It will move up. Ionization will also move up, but not as much, and therefore the critical energy will go down. And this position of the critical energy is where we see most of our particles, and they can be matched, for example, to the acceptance of the detector readout, photomultipliers, and so on. Okay, now let's change topic. A similar discussion to what we had before, multiple scattering and MOLIÈRE theory. This applies to both electrons and muons, but makes most sense if we talk about interactions with the nucleus. So we now consider what happens when a particle coming from the left here travels through a detector and experiences multiple interactions. So we zoom out a little bit. These are finite-sized detectors now, and both BREMSSTRAHLUNG and ionization deflect the trajectory of the particle, and so it moves around in a more or less random direction until it leaves. The statistical treatment of these multiple scattering processes is called MOLIÈRE theory. It's nature, it's a statistical mechanics. We only go through a few of the results that are relevant for detector design. I'll have an example on the next slide. Let me just say what the main results are. So we talk about a particle and its deflection when going through a slice of the detector. We know that the processes like Rutherford scattering have 1/sin² theta divided by 2 dependence. So in some of the cases, we see a very large deflection. That is was already the source for the creation of delta electrons and a large tail in the energy loss when the detector is thin. Now we look at what that means for the deflection of the particles when they travel through finite-sized detectors. So the theta plane angle describes the angle of the deflected particle after it has traveled through a detector of size x. Now, MOLIÈRE theory predicts that for very thick detectors, one expects a Gaussian distribution for the angle here with a width parameter of theta 0. Now, this Gaussian resolution parameter, we can compare theory and experiment if we take the logarithm of this distribution and we make the distribution with respect to the square of the angle. This Gaussian distribution will be a linear falling function. So it means that for most of the deflection angles, actually the Gaussian theory is a very good approximation. However, MOLIÈRE theory predicts large deviations for large angles. And these large angle scatterings, these are the ones that happen with a high momentum transfer, low impact parameter, and high values for the deflected angle. So impact parameter is low, almost head-on collisions, but the outgoing particle is deflected a lot. So here we see this increase in the spread of the angular change in direction when a particle goes through a finite-sized detector. Now, the treatment is something in between of quantum mechanical calculation and empirical treatment. I put here the so-called Highland formula that gives you the energy spread as a function of the thickness and as a function of the ratio of the thickness of the detector versus radiation length. You don't have to learn this formula because if you're designing a detector, you're anyway going to look it up and do a more accurate treatment. But the important statement here is that the ratio of the thickness of the detector to the radiation length is what characterizes the deflection. So let's look at it in practice, okay? What does this mean, for example, for the resolution of a secondary vertex? Now, consider again, for example, it can be E plus E minus or hadron-hadron collisions. And we want to identify displaced particles. For example, a big quark produces B mesons. B mesons have a picosecond lifetime. Picosecond lifetime with GeV mass and a high momentum can lead to millimeter displacement. So now we want to measure a millimeter displacement. The B meson, the candidate, traveled here invisibly and decayed here in the secondary vertex. The primary vertex is where the hard collision happened, for example, plus or minus or proton-proton. So this position is known with very high accuracy. And now we want to determine the position of the secondary vertex with good accuracy to infer whether really there was a displaced vertex or whether this was just a mismeasurement. Now, the example given here is a 10 GeV B meson with a 1.5 picosecond lifetime and a 2 millimeter distance of expectation for the distance of travel, the beta gamma c tau. And by measuring that accurately, we can infer the presence of the secondary vertex. Now, what will happen is outside here, let's say there is a detector signal coming from a pixel or a silicon strip, which is a few centimeters away from the beam pipe. Assume that the beam pipe has a diameter of 50 millimeter and a thickness of 1 millimeter. Assume that the B meson decayed, for example, to pions, and the pion now has a momentum of 5 GeV. This is not unrealistic. 10 GeV B, and then eventually you get a pion with 5 GeV, and you want to measure now the direction of this pion, because with the direction of this pion, you will get the impact parameter. I put, for this example, I put the numbers here for two different materials of the beam pipe, because that's what we want to choose. We want to choose the material of the beam pipe such that the resolution of the impact parameter is good enough so that we can make an identification of the secondary vertex. The resulting resolution delta D is the theta naught, which is the parameter from MOLIÈRE theory here, because this is the average angular spread. So it's the average angular spread times the distance of the beam pipe where the deflection happens. So we think of our pion going through a 1 millimeter beam pipe in a distance of 50 millimeter from the center. And so the impact parameter resolution is to good accuracy given by the angular spread from this MOLIÈRE multi-particle scattering in the beam pipe times the distance to the beam pipe. Numbers are given here, and the comparison is between aluminium and beryllium. And these two materials are the ones that were in question for the LHC beam pipe, and you see that theta naught and theta naught, the angular spread, and delta D, the impact parameter resolution, reduces by a factor of 2, just because we choose a lower C. We choose a lower C material of the same thickness, because a lower C material which will give a lower angular spread, and because C enters with the squared in BREMSSTRAHLUNG processes, this is what this small design change improved the impact parameter resolution by a factor of 2. Now it's a small design change. I put here the actual measured impact parameter resolution as a function of the momentum of the particle, just so that you get an idea. We have typically hundreds of microns, tens of microns That's the ballpark resolution for this impact parameter. Now, it's a small design change. I mean, a designer takes a second to change the specification from aluminum to beryllium. However, beryllium is very difficult to handle. Before the LHC, beryllium could not be welded. And the welding of these low C materials, beryllium in particular, had to be invented just to construct the beam pipe so that our impact parameter resolution would drop so that we could, with a better accuracy, infer the impact parameter and the position of these secondary vertices here. So that's how MOLIÈRE theory, multiple particle scattering, at a very low level interfere with detector design. In this case, the choice of the material for the beam pipe. Good. Now we change topic again. Of course, the study of interaction of particles with matter is a collection of physics that you may have learned or that you should have learned in the introductory courses or the first half of your studies. We now talk about the electromagnetic field in a dielectric medium. So far we've studied ionization and BREMSSTRAHLUNG. Now we study the energy loss that comes from the emission of photons and the electromagnetic interaction inside a medium. Now, I decided not to derive the equation for the relative permittivity in a medium. If you follow the link given below, you get an excellent introduction. It's not needed in detail. What you need to, but it does pay off to look at the formula for a little bit. So the relative permittivity is a complex number, and it gives you the electric field in the medium with respect to an incident field in the vacuum of a certain frequency omega. And it's a sum of the responses of many harmonic and material dependent oscillators. Now, there is a dispersion relation that holds in matter. Omega squared is k squared c squared over epsilon. Square root of epsilon is n, and if the absorption is small, this means that the speed of light in the medium is smaller than the speed of light in the vacuum. What we can do is we look at the behavior of the permittivity and hence the electromagnetic field in the medium as a function of the frequency of the wave. The bottom plot here shows this behavior as a function of the wavelength. The top plot here shows the same behavior for a single resonance, but this is in terms of frequency, so they are reversed. High frequency means low wavelength and vice versa. So high energies are here to the left. What we are seeing is that for very high frequencies, above all atomic and molecular resonances, the n, the refractive index, is smaller than 1, but it is very close to 1. It very quickly approaches 1. This is because very high frequency waves cannot excite oscillators. They are practically traveling through vacuum with very small interactions with the atomic and molecular modes. At very low frequencies, all these resonances are driven a little bit. N is larger than 1, which means that the speed of light, the speed of light in the medium is smaller than the speed of light in the vacuum. Now, it remains to be discussed what happens at the resonance, but we already discussed this, because at the resonance is where the ionization takes place. We talked about ionization in terms of the Bethe-Bloch equation, but ionization is the resonant. Ionization is a resonant interaction with the electrons in the atomic shell. What one has as a function of energy is a growth, then a sudden drop, and then growth, a sudden drop of the permittivity as a function of the frequency. This is the region of anomal dispersion. And then the permittivity rises again. In this narrow peak region, the imaginary part is large, which is indicative of a large absorption. So the field gets, the photons get absorbed. Good. This region of anomalous dispersion is flipped here because the plot to the bottom left shows the refraction index as a function of the wavelength, not of the frequency. So this should be a very qualitative repetition of electrodynamics in matter. Let's look at what a single photon does. We want to move towards an understanding of effects like Cherenkov radiation. So let's write, and I hope my pen now will work. Let's do our usual relativistic calculations. These are more simple than what we've done before. Let's do our relativistic calculation. I am now trying to share my screen, and I think my pen works. Start to share. Yes, I'm sharing. So far, so good. And I'm writing. That's excellent. Okay. Now we look at the electromagnetic field in a dielectric medium, and we consider single photons. Now let's have our particle. Oh. There we go. Travel and emitting a photon, and we want to know about the angle. For example, the angle this photon can be emitted. Now, we start as usual by writing the momentum in a certain useful form. So m is the mass of the particle, and we choose c and v as the components of the vector. We can rewrite this mc gamma 1, 1, and beta, as you know, or we can also use E over c and the momentum. And we can compute p squared. That's of course mc squared gamma squared times 1 minus beta squared. This is 1. I'm repeating here what we already discussed, and that equals E squared over c squared minus p vector squared. Nothing new has happened so far. Now we write for the momentum of, that was the momentum of the incoming particle. Now we write for the momentum of the photon, make an ansatz, h bar omega over c, because h bar omega is the energy of a photon, and h bar k. So here we have only used the basic relation for the energy of quanta of light. The energy is h bar times omega, and the momentum is h bar k. That's all we have to use. Let's see. We know that p prime is p minus p gamma, and we can square this. And we're going to find m squared on the left and m squared minus 2 over c squared. I divided by c squared times p in p gamma. So because this goes, we know that this has to be 0. And what is it that has to be 0? We can now write this in components. And we use the forms of the momentum for the incident particle and the photon as given above. So we know that E over c times h bar omega over c minus h bar times k in p, this must be 0. Which means that we can deduce omega equals k in p divided by E over c squared, which we can now rewrite in a little bit more favorable fashion as c times k times p over E over c. And with p divided by E over c, we use our different representations of the form momentum of the incident particle to write here c times k and mc gamma beta divided by mc gamma, which means most of this cancels. This is just k times c times beta. So it is actually k times the velocity of the particle. It's interesting that the velocity appears here. I mean, it's important that the velocity appears here. These are still in products. We can now write this as k times v, the magnitude, times cosine theta c. I give the angle an index c because Cherenkov was the first who derived these equations properly, albeit in a more realistic setting. Nevertheless, we now have an expression of omega in terms of the angle, and we can now relate this to our dispersion relation. Omega squared is k squared c squared over epsilon, and therefore the wave number is square root of epsilon times omega over c. And we can now put the two equations together and write omega equals square root epsilon times omega over c times v times cosine theta c, and suddenly omega cancels left and right, and we find 1 equals square root epsilon v divided by, that is a mistake, v divided by c times cosine theta c, or yet in other words, this angle cosine theta c equals 1 over beta times n. And this is important because you know that the quantity to the left is something between -1 and +1. So you will have a real solution only for certain values of beta. In particular, and let me now stop my sharing here and let me share again. 1 second. I need to find my, here we are. Let me share my desktop again. In particular, this equation does not have a real solution unless the velocity of the particle is larger than the speed of light in the medium. In case this condition is satisfied, we do have a real solution for the frequency and the wave number of the photon, and a real photon is exchanged and created, and we can detect it. For too low values of the velocity, this does not happen and no photon is created. Moreover, we used that the square root of epsilon is a real number, but in truth, it is a complex number which has an absorptive part. So as long as we have a sizable absorption which is close to the resonance, we will not find a solution. Finally, in the very hard UV, so very high, for very high frequencies, n is 1, or is very close to 1. And if n is very close to 1, or square root epsilon is very close to 1, the speed of light in the medium and the speed of light in the vacuum is the same, and the speed of the particle cannot be larger than that. And hence, close to the resonance because of ionization, or in the very hard UV, there is no real solution, and hence no photon will be emitted. Good. So this tells us that for high velocities, higher than the speed of light in the medium, and we want to have a large value of n to see that, real photon is indeed emitted. Now, this is called Cherenkov radiation, and we're going to discuss it, but let's first look at the transverse reach of the photon of this electric field in the electromagnetic interaction. Now, let's assume that the wave number x, that the wave number has no component in the x direction. This is not a loss of generality. So we are again in a situation like here with, we just put our coordinate system y at the top and z to the right. Now, let me share again, because now we're going to calculate the transverse field, the reach of the transverse field that's created by a particle that moves in a medium. I can only do it if I manage to share. Yep. And I think that's the last calculation in the lecture or so. Almost. So I'm sharing. And let's start a new. We start a new window, and we calculate. This is also this calculation is also only for your education. It will not be part of. It will not be part of the exam because it teaches an important point, but it's not the basis of many further calculations that we're going to do. But let me stop with the general remarks. Let us write down what we know. So we said that kx equals 0, no loss of generality here. And we know that omega is therefore V times kc, which we can write as V times k times cosine theta c. That's one thing we know. The second thing we knew, and we already put this together for the threshold above which real emission is possible, but let's write again, omega squared times epsilon divided by c squared, our dispersion relation, but this time without the kx to simplify the calculation, plus kc squared. So let me make a drawing here. We have a particle of mass m, and it emits a photon. The case of real emission is described by the emission angle theta c. But now we look at the case when there is no real emission possible. So the following calculation is characterizing the electromagnetic field if there is no real emission possible. We want to still classically derive the electromagnetic field, but since no photon is emitted, it will have a finite extent. So to that end, we start with the computation of ky squared. We do not expect to find a real solution now. Ky squared is, following from the second equation, w squared over c squared times epsilon minus w over v squared, and this becomes w over v squared times v squared over c squared, that's one way to write it, minus 1. You don't have to remember the tricks, but I'm nevertheless showing them. It becomes omega to the v squared, and now we absorb the epsilon in the speed of light in a convenient way. So we divide the v squared by c, which we again divide by square root epsilon minus 1. And we call this beta prime. Beta prime is the velocity divided by the speed of light in the medium, and the speed of light in the medium is the speed of light divided by square root of epsilon. Just that you know, but beta prime can be larger than 1. It can be larger than 1. For real emission, it has to be larger than 1. We calculate, therefore, we write, therefore, k, it's not ky, k mu, it is so used to writing momenta. This is a wave number, it's ky, is omega divided by v, beta prime squared minus 1, and then the square root of this quantity. And for real emission, this has a real solution, because real emission is beta prime greater than 1. But now we wonder what happens for beta prime smaller than 1. So if we do not surpass the threshold of real emission of photons, we do not radiate so-called Cherenkov radiation, it's this smaller than 1. In this case, we take a plane, we view the radiation as a plane wave. And a plane wave is described by e to the I omega t minus k k in R. And we pick out the y component here because the y component will now be imaginary. So let's do it. It becomes e to the I omega over v times c minus vt, which describes a wave propagating with velocity v in the c direction that comes with the particle. And then we simply write here e to the minus y, that's the coordinate, and we divide here by y0. Note that there is a minus here, and this minus 1 is the I squared, and I squared comes from the I that appears in front of the k naught, ky, in case beta prime is smaller than 1. Oh, I already wrote this here. In case beta prime is smaller than 1. And therefore, we only need to flip the sign inside the square root. And because we wrote this in the denominator, we immediately find y0 is now, I need to invert the chi naught here. It is therefore v over omega times 1 over square root of 1 minus beta prime squared. So this is the reach. This is real if beta prime is smaller than 1. Therefore, we now know the reach of the electromagnetic field for a particle that travels with a speed that is smaller than the speed of light in the medium. It has a finite transverse reach. The wave equation, that's called an evanescent wave in electrodynamics. The wave equation does not have an imaginary exponent. However, we pick out the I, we take the I that we pick out from the imaginary solution of the wave number to predict an exponentially falling distribution in the y direction. So this is the reach. Now it's not in a very useful form. We can rewrite this to make it a little bit more useful. Again, we look at our dispersion relation. We take the dispersion relation was omega equals ck over square root of epsilon, and now we write the ck as omega naught divided by square root of epsilon, and this guy, the omega naught, is the angular frequency in the vacuum. That's the angular frequency that a wave would have with wave number k if it traveled in vacuum. So this is the angular frequency if we were in the vacuum. We are not, but we nevertheless use this quantity. Then we define k naught, which we define as omega over c, which is k over square root of epsilon, and that's the wave vector. That's the wave vector for a wave with frequency omega, if this wave was in the vacuum. So in other words, the two quantities omega naught and k naught are related to each other with the vacuum, dispersion relation, and that helps us rewrite the transverse reach. Let's do like this. Gamma 0, it was, I'm copying from above, v over omega divided by 1 over square root of 1 minus beta prime squared. Now we call this here gamma prime. That's the gamma factor, relativistic gamma factor, related with the beta prime in the medium. We now rewrite the v over omega as v times square root epsilon divided by omega 0 times gamma prime. And now, because beta prime is v over c divided by square root of epsilon, this becomes c over omega naught times beta prime times gamma prime, which is 1 over k times beta prime times gamma prime. And that's what I wanted to show to you. The transverse reach of the electromagnetic field is again a function of beta prime and gamma prime, so beta times gamma, but evaluated in the medium. This explains the beta gamma dependence, by the way, of the density correction in the Bethe-Bloch equation. But now I unshare. And I show to you the same material very briefly in the slides. I hope you have them open anyway. Share, yep. Okay. So to repeat, what have we found? For beta prime larger than 1, which is possible if the particle travels with a speed larger than the speed of light in the medium, now we have a plane wave solution that's real, and the field, of course, it extends indefinitely in the y direction. It's given by our original plane wave solution, corresponding to a single photon emitted in in the direction phi c. However, for beta prime smaller than 1, we have an evanescent field, so a field with a finite extension of a characteristic distance y0 that's given by, again, by our factor beta gamma. So for ultra-relativistic particle, the beta prime, for not ultra-relativistic particles, for particles that approach the Cherenkov threshold, which is given by beta equals 1 over n, the field begins to extend towards infinity, and above the threshold, a real photon is emitted. Okay, so now we do understand a little bit more about electromagnetic radiation created by a particle that goes through the medium. Let's look at the boundary in between that I alluded to at the end here. What happens at the boundary? This is when we just about create a real solution. Below so the threshold for a real solution to exist is that beta has to be in excess of n, so that the argument in so that it can be on the right hand side of a real valued angle in the cosine. In this case, Cherenkov radiation is emitted. Now we can take this to the extreme and consider an ultra-relativistic particle that enters the medium. If n is square root epsilon is smaller than 1, we will have exceeded the speed of light in the medium, and there is a maximum angle corresponding with there's a maximum angle under which the photon can be emitted, and this is a material dependent property. It's the inverse cosine of the inverse n. So theta max is cosine is arcos cosine, as we say in German, I believe, of 1 over n. Now consider this image here. we have a particle that's traveling here at the center and it travels forward. It moves faster than the speed of light in the medium, and hence a shock wave of light develops. It's emitted at an angle of theta c that corresponds to this material dependent that corresponds to the theta max as a function of the refractive index, and this creates rings at photosensitive detectors. Below here is a beautiful image of a Cherenkov ring. A charged particle, I think it was a proton, went through a short strip of material. I believe in this case it was silicon, and produced a beautiful ring of Cherenkov radiation that was recorded here with a very fine grid of photosensitive sensors. Now, it is to say, Cherenkov radiation, we will talk about Cherenkov detectors in a later lecture, not a lot, because these are very complicated devices. They are not used a lot, only for special purpose applications. It's hard to record those rings, just because the geometry of the detectors is difficult to assemble. Usually one sees only parts of the ring and so on. It is sometimes useful, however, to only check whether photons have been produced at all. Those would be Cherenkov threshold detectors. Cherenkov ring imaging detectors are much more difficult to assemble. Now, let's look a little bit into what the properties of Cherenkov radiation are. There is a minimum energy of the particle above which Cherenkov radiation is emitted. So I don't have to write this down because that's completely straightforward now. The threshold energy of the incident particle is calculated by considering the relativistic gamma factor. Write it as 1 over square root of 1 minus beta threshold squared. And now the beta threshold squared, it is the threshold is achieved when the argument of the cosine top right here equals to 1, and that's achieved when beta threshold is 1 over n, and since it enters squared here, this becomes 1 minus 1 over permittivity, and if we insert back the n, it's just n over square root of n squared minus 1. Typical values for n for relevant detector materials are 1.5 or so. So not too high, 1.5, 1.3, sometimes 2. We'll look at the table on one of the next slides. Not too high values for gamma are required until Cherenkov radiation is emitted. Now we can compute the maximum angle that this radiation is attained for. In fact, we almost did. It's conveniently calculated from the sine, which we write as 1 minus cosine squared, and the cosine squared of the maximum angle is derived from the equation for in the limit of beta equal to 1, which just becomes 1 over n squared, and and that sine is given by that the sine of the theta max angle is 1 over gamma threshold. So if we choose a material with a high value of n, we will see radiation for lower energetic particles that are also emitted at large angles. Now we can finally compute, but I don't go through the details here. I don't think this is necessary. I put here the calculation for completeness and because I wanted to understand it myself. This is the angle of radiation for a given beta now. We've so far talked about the limiting cases when the beta is just above the Cherenkov threshold and when the beta equals to 1, so when it is close to the speed of light. But for a fixed beta, one can calculate by completely trivial and straightforward substitutions of the type that we've done on this slide, that it is that the sine squared of the actual emission is the sine squared of the maximum, the sine squared of the maximum emission divided multiplied with a factor that is smaller than 1. And this explains why we see rings, because it's more likely that the emission happens closer to the maximum value and then it is attenuated. And this predicts the appearance of Cherenkov rings, which took a while to see. Good. One thing about Cherenkov radiation, it is very weak. It's only 0.1 or 1% or so of the yield of ionization. It has a few interesting properties. First of all, from the knowledge on the material, one can measure, with the size of the rings, one can measure the speed of the particle, beta itself. Usually, oftentimes we measure the momentum, but if we measure the momentum and the speed, we can make a particle identification. So Cherenkov ring detectors are often used for particle detectors. It is also emitted promptly. That means at the moment the particle travels through the material, so one can use it for timing. That's in contrast to scintillation and ionization signals, because both the scintillation and ionization signals are deposited somewhere in the material, and the signal does not travel with the speed of light like the Cherenkov light does, but rather stays in place and then drifts. So timing for Cherenkov light has a better resolution, just because you depend much less on material properties. There's no drifts involved, it's just the light that's emitted promptly. Good, that's what I wanted to say about Cherenkov radiation. The last interaction of matter, of charged matter, of charged particles with matter is transition radiation. We don't do any details here, but only give a very heuristic treatment. Nevertheless, transition radiation is an interesting property of detector physics, which are with a range of interesting applications. Now, think of the following. We have two different refractory indices, one left and one right. The particle now traverses a surface where the speed of light in the medium changes from n1 to n2. If you solve the vacuum equation, if you solve the Maxwell equations in the material, you find that for a relativistically moving particle, you will find these star-shaped field lines, and the spread of these field lines will depend on the material property n1. So it will be different left and right. In other words, the electromagnetic field for a charged particle, when it traverses from left to right, it has to rearrange itself. And the rearrangement causes the emission of highly energetic photons. You can imagine probably that in this idealized situation allows calculations from first principles. And indeed, this is the case. If you look at the references I give at the beginning of the lecture in Kolanowski, you find 20 pages or so of calculation of the emission of transition radiation. It's just because it's doable and it's fun, but we're not going to do it because it takes too much time. And heuristic treatment is enough. So the most probable emission angle for transition radiation is very narrow to the trajectory of the particle. It's confined to within typically 1/gamma, and we often have particles with a gamma factor of 1000 or so. Just think of relativistic electrons, for example. And the intensity is proportional to gamma. So the transition radiation increases mildly, so linearly, with the gamma factor. For ultra-relativistic particles, the frequency of the transition region is in the hard UV, and it is, because if it's greater than, gamma is greater than 1000, is very closely collimated with the particle that causes it. Measuring the intensity, therefore, means we measure the gamma factor of the particle, and if we know the gamma factor, we know the speed. If we know the speed and the momentum, we can identify the charged particle. Here is the top right plot shows the angular emission profile of transition radiation in mylar foil. This is a fancy word of plastic. This is just plastic. So in a plastic foil, it's important that the material must be transparent for the transition radiation that is emitted. There is no use for transition radiation if the material absorbs it. But this can be achieved with, for example, with fleece radiators. So fleece is just an amorphous bundle of fibers. Those fibers can be plastic. And now we have protons going through the detector, and we get electrons going through the detector. This is the situation in the space-based AMS experiment. In the International Space Station, you don't have a lot of current. You cannot power you cannot power large magnets, because the only thing is you have is batteries with finite lifetime and solar powers. So one has to do particle identification with detector components that may use high voltage, but they do not need high current. And the assembly shown here is an example of that. You see here a fleece radiator with with a large refractive index and protons and electrons going through. Now you have measured the momentum of these particles, but now if you find a transition radiation photon that can be recorded here in these drift tubes, which we are going to discuss next time, because these are gaseous detector, which operate with a single high voltage, you can discriminate the protons from the electrons. Because transition radiation goes with gamma, and the gamma factor for an electron is much higher than for a proton at the same momentum because of the different mass. So sometimes transition radiation can be put to very good use. Atlas also has a transition radiation detector. We'll talk about this when we talk about Atlas. We are done now with the interaction of charged particles with matter. We've spent now 45 minutes talking about the photons that are emitted from the charged particles when they traverse matter. Now we talk about photons themselves. It will again be a heuristic discussion, and it's based on principles that are by now familiar to us, I think. We already said in the beginning of the morning lecture today that for highly energetic photons in material, they can interact by absorption, and if it's absorption, we get an exponential reduction of the particle multiplicity versus the penetration depth in the detector. Let's now put together the different effects a photon can interact. A photon interacts with matter. Now, one is the photo effect, and it's relevant for the absorption. A quantum mechanical calculation shows that the photo effect scales with c to the 5, but it falls very quickly with energy. It falls with roughly with a power of more than 3. So the exponential law is only valid for intermediate, not too high energies. The photon loses in this case its complete energy, and instead an electron is emitted. At a little bit higher energies, a Compton effect takes over. The Compton effect is the scattering. Compton effect is the scattering of a photon at an electron in the atomic shell. So the electron, we imagine this in an S-channel diagram, for example, the electron picks up the photon and emits it again. Because this is incoherent, this process is proportional to c, the number of charges in the nucleus and the number of atoms in the shell. And at the very highest energies, above the pair production threshold of 2 electrons, pair creation can take place. This process is proportional to c squared because it can only take place in very strong fields close to the nucleus, and close to the nucleus is so small that well, if the nucleus is smaller than the wavelength of the photon, then pair creation will coherently be the dominant process. So we have, in summary, the photo effect with secondary emissions of electrons. Then there's also the Auger electrons and everything that's relevant for quantum mechanics of ions. Then we have Compton effect, the simple quantum mechanical process interacting here just with the contribution from the individual scattering, elastic scattering events with the electrons in the shell, and finally pair creation. The top right plot shows an image from a large bubble chamber at Fermilab, where you have all these different processes. For example, it's fun to look at all the trajectories here and try to figure out what has happened. This guy here is nice where my mouse cursor is. It's a positron, which you can tell from the curvature. It gets annihilated. A highly energetic photon does not produce a drag, and this does not ionize. And then it hits a nucleus, and the pair, an electron-positron pair, is created. So that's what we imagine is happening if when electromagnetic interactions in matter take place. Now let's sum up the interactions for the photons. The photo effect increases when the energy passes, so this versus energy. Energy is frequency. High frequency means low wavelength, and if the wavelength is low and the threshold is passed to excite a nuclear shell, we see here these characteristic material-dependent edges corresponding to the corresponding to the individual shell. This example, this example is lead with C of 82, so one of the highest C materials that we conventionally use. There is also Rayleigh scattering, which is elastic coherent scattering at the whole atomic shell. It is a small contribution. Then there is, for medium energies, talk about MeV here, Compton scattering, but above 1.22 MeV, which is 2 times the electron mass times c squared, the photo effect takes over. I'm sorry, pair creation, I said it wrong. Photo effect dies out, pair creation takes over. Typically for hadron, for state-of-the-art hadron colliders are in the GeV regime. That means if we try to identify and reconstruct and detect photons, we typically are in the GeV regime, so that's somewhere here. That means the first interaction in the detector will be an pair creation event for photons. Now, in principle, we could do calculations for pair creation, but look at pair creation. When does it happen? We have a nucleus, we have a photon. If they are close, they can create a pair. Now flip the photon line with the electron line. You get the Feynman diagram for BREMSSTRAHLUNG, okay? An electron interacting electromagnetically with the nucleus and radiating off a photon has the same particles. It's just different initial and final states, but the exact same particles are appearing in the Feynman diagram. That allows you to calculate the mean free path of a photon in terms of the electron x naught in the same material. The photon mean free path is a little bit larger than the electron. This factor 9/7, it comes from the Feynman rules applied to the initial and final state here. When an electron has lost 63% of its energy on its travel through matter, a photon has only lost 54%. But otherwise, electrons and photons in the detector behave very similarly once they are in the detection material. Let's put things together for the photon total cross-section. Again, we have based on coherent and incoherent, coherence and incoherence for the different processes, we have different photon total cross-sections. The left one shows a low C material, carbon, for example, C equals 6. The right material is lead, C equals 82. You see that the pair production grows with C squared. The axis on the y-axis is Barnes, but it's logarithmic. So you see that well, what you see is that pair production, when you go from low C to high C, pair production grows. The Compton interaction is only really relevant in the MEV regime for low C. For low C absorbers. It's not very relevant for lead because pair production is just so much larger. And here we have the photo effect, which with this characteristic edge-like structure. There's of course many more edges if you have more more atomic shells. So that's the material dependence for photons. And now let's compare. We take one more step away. We look at things for the distance. an overview of all the electromagnetic interactions for photons and electrons. Again, photo effect with its edge-like structure, it falls. Then Compton effect proportional to C, maybe in the MEV regime, and pair creation above an MEV or so. For the electrons, we have an ionization contribution that is, however, completely surpassed by the BREMSSTRAHLUNG, which goes with C squared of the target material. And if you remember, we had to divide by E to put it on a useful scale. Now, if we put ionization and BREMSSTRAHLUNG on the same scale, we see that the energy loss is linear with energy and will completely dominate. The last comment here is that BREMSSTRAHLUNG scales with the ratio of masses squared, which is 40,000 when you go from the electron to the muon, which makes BREMSSTRAHLUNG for muons negligible, and for muons only the Bethe-Bloch-like ionization energy loss is relevant. So we've discussed all electromagnetic interactions now, and their Z behavior, and mostly their energy behavior. And that's a good basis for discussing detectors, but we do still have to discuss hadronic interactions. Hadronic interactions are a different game. Much less is known because of the strong interaction, the short-range nature of the strong interaction, and the inelastic nature of the collisions. One can treat those collisions only statistically. The strong force is short range, and that's the reason why that is so. Look at the target nucleus here. Look at an incoming hadron. This incoming hadron will, the incoming hadron can be anything, can be a kaon, a neutron, a proton, or whatever. The nucleus is the target material in the detector. This incoming hadron is a typical particle in the jet, for example. And we've already looked at the composition of jets in terms of hadrons. So we already know that the population of incoming hadron, it really spans all metastable QCD bound states that are allowed, lambdas, kaons, whatnot. So that family of particle hits the nucleus and produces plenty of cascade interactions. Crucially, it can produce pi zeros. And a pi zero have the property that they decay into photons. And hence, at the beginning of a hadronic interaction, important first few steps happen. The amount of pi zeros that are created determine how much electromagnetic energy is radiated, because you start with hadronic interaction, it may happen that most of the energy, like, I don't know, 80%, is transferred into hadronic pi zeros. The pi zeros decayed electromagnetically, and you are back in the electromagnetic interaction, because these are now high energetic photons, and the detector cannot know where this photon came from. On the other hand, it need not be so. It could be that protons, neutrons, pi zeros, and kaons are produced, and you get a cascade development of hadronic interactions. This cascade decay then produce other hadrons with lower energy. Eventually, a shower develops, a shower of interactions with different time scales. So you have the incoming hadron comes with the speed of light, produces a bunch of particles with a fraction of the incident energy. They produce secondary and tertiary and whatnot interactions. They can have 10 or so stages. At the end of the day, you have excited nuclei with a time scale of 10 to the minus 22 seconds for spallation and evaporation of neutrons, alpha particles, protons, and photons, in case you produced an isotope that's a gamma radiator. and 10 to the minus 18 seconds de-excitations in case you excited an internal excited state of the larger of the nucleus. So these secondary hadronic decay products, they cause shower formation. Then the fraction of neutral pions, as I've tried to explain before, the fraction of neutral pions produced along the way is the origin of electromagnetic showers that are produced alongside with the hadronic ones. And because the spread between electromagnetic and hadronic energy it's unforeseeable, and it's also widely fluctuating. That means that hadronic showers are very difficult to model. Some shower may have 90% of energy in the electromagnetic sector. The next shower may have 90% in the hadronic sector. And the electromagnetic calorimetry and the hadronic calorimetry and other subdetectors react completely differently to photons or electrons produced from pions or protons and neutrons. These signals are different. That we've discussed. So the main message here is that hadronic interactions are complicated. They come in showers, and those showers fluctuate widely. Okay, we will discuss this next time. It's 3 now, and I've almost lost my voice again. Next time we start with the description of hadronic and electromagnetic showers. I want to anticipate the typical behavior here. The hadronic interaction is strong, but it is a short-range interaction. It only happens in the nucleus. Again, an exponential law is an excellent description. Similarly to the radiation length for hadronic interaction, we have an absorption length. Now, we know that, and we can anticipate, we're going to discuss it, that an electromagnetic shower is much more foreseeable. That's just because we could predict very nicely all the ionization, BREMSSTRAHLUNG, photo effect, Compton effect processes, and all these have a smooth energy dependence. So above a certain energy, you will just have pair creation. Below a certain energy, you'll have Compton scattering and secondary ionization. That gives a predictable and short scale, and that gives a predictable electromagnetic shower on a short length scale. However, if you have a hadronic interaction, you can produce, first of all, you can of course produce electromagnetic showers, and you see those inside here. There are electromagnetic shower components that look like here but spread out, and the spreading out comes from the hadronic component. For example, a neutron, which is not electrically charged, can travel a long distance in the material. This is both ion and it's both simulation, but the neutron can travel a long distance and then suddenly lead to violent subsequent shower collisions. And because of this neutral hadronic fraction and the highly fluctuating electromagnetic yield in the first or so reactions, these hadronic showers go much deeper and look and the next one might look completely different. And that's what makes the reconstruction of hadrons much more difficult than electrons and photons. But here I stop. There's not much left to be done for next time. And then we start with detector physics. Thank you for your attention. I switch to German for a few seconds.